Hello everyone and welcome to our video on waves. In this video we're going to explore properties of waves, types of waves, wave speed, sound waves, and the Doppler effect. Let's start out by looking at a common wave that maybe you've experienced in everyday life, maybe at the stadium, where the crowd's going wild, they're supporting the team, and they do the wave. We all know how the wave is done, but I'd like to show you a video of a crowd doing the wave here. So, as you see that wave traveling around the stadium, you got to ask yourself, what is actually moving? Is there something physical moving through the stadium? Is some physical matter traveling through the stadium? And if you think about it, the answer is clearly no, because there's no physical object that's moving around the stadium. And yet, clearly something is moving. The question is, what is moving? And the answer is quite interesting. If you think about this motion, this up and down motion with the wave, that is actually a representation of energy. When the hands go up and down, that represents kinetic energy. And so what a wave is a transmission of energy. And so we want to say waves transmit energy. The next question we want to investigate is what causes waves? And it doesn't matter if it's a light wave, if it's a sound wave, or a ripple on a pond. It turns out that the same phenomenon causes waves. So let's take a look at another video that I think illustrates that really nicely. Here we go. In this video, we're going to see a coil of string to unroll some paper. We're going to see a spray paint can on a spring, and you see that the scientist here is going to let go of that spray paint can. We all know the mass on a spring is going to oscillate up and down in simple harmonic motion, and look at that. As he unwinds the paper, you see the pattern that's traced out on the paper is a wave. So what causes waves? It turns out oscillations. Oscillations create waves. So let's write that down. Waves are caused by oscillations. Another word that we want to start to get familiar with is the word propagate. And the word propagate simply means to travel. So often you're going to hear people say the wave is propagating through space, or the wave is propagating through time. Propagating is simply a word that means to travel. Okay? And what we want to do now is look at the two types of waves. So the first type of wave we want to look at is called a transverse wave. And what we want to do first is look at the definition of a transverse wave, then we're going to look at some examples of transverse waves, and then we're going to diagram out a transverse wave. So the direction of oscillation in a transverse wave is always perpendicular to the direction of wave propagation. Now let me give you a really nice example of this. So in this simulation, what you see is there's an oscillation on one end of this spring, or this string right here, right? This green dot that you see all the way to the left is oscillating up and down on this piston. So this piston is moving up and down, and what you see is that the wave is being produced on this string. Now the direction of the oscillation is up and down, right? Clearly the direction of the oscillation is up and down. But the wave is traveling to the side, right? The wave is traveling this way. So that means that the angle between the direction of the oscillation and the direction of wave propagation is 90 degrees, which means they're perpendicular, right? So what we're going to say in a transverse wave is that the direction of the oscillation is perpendicular to the direction of the wave propagation. Now, some examples of this would be waves on a string. So if you play a musical instrument on a stringed instrument, like a guitar or a ukulele or a violin, whenever you pluck that string, you're creating a wave on that string, and that is a transverse wave. Other examples of transverse waves would be ripples on a pond. Ripples on a pond. And another example is light. So light itself is an electromagnetic wave, which we're going to study, and light is also a transverse wave. So the next thing we want to do is try to diagram a transverse wave. So once again, if we go back to this simulation, you see here that the oscillation is up and down, right? So in our notes, we want to represent the oscillation as an up and down motion. So if you want to label this oscillation, that's a good idea. So this double arrow represents an up and down oscillation. And from this oscillation, we can see that the wave is traveling to the right. So let's try to illustrate that in our diagram. Let's have a wave traveling to the right. So here's our wave. And we're going to give this wave a velocity vector, okay? Let's put a velocity v on the wave to show that the wave is traveling to the right. And we can see that the oscillation's up and down, the velocity's to the right, and the angle between up and down and right is 90 degrees, and that's where we get the perpendicular from. All right, good deal. Let's move ahead. The next kind of wave that we want to look at is called a longitudinal wave. And in a longitudinal wave, the direction of the oscillation is parallel to the direction of wave propagation. And I want to once again show you a simulation of this. So in this simulation, what I'd like to show you is a longitudinal wave. Now, let's see if I can center this a little bit. There we go. Okay, so in this simulation, what I'd like to show you is that the oscillation of the red object turns out that this is actually a representation of a speaker. Okay, so it could be a speaker on your TV or in your headphones, but anytime sound is produced, there's an oscillation, in this case, back and forth with that red membrane that you see there. That oscillation is sideways, right? We can clearly see that the red membrane of this speaker is oscillating back and forth sideways. And look at the direction of the wave propagation. So when this speaker head hits all these air molecules, those little dots, those black dots that you see there, those are air molecules, right? So when the speaker hits those air molecules, it compresses those air molecules, right? So it's pushing the air molecules over and over again. And you see the ripples. These ripples of air molecules that are condensed by the speaker are propagating through space. Now look at the angle. The speaker head is oscillating sideways, the wave is traveling sideways, and that's how we get to the conclusion that a longitudinal wave has a direction of oscillation parallel to the direction of wave propagation. So the most common example of a longitudinal wave is sound. And in addition to sound, we can say any kind of pressure wave, like a shock wave. If there's an explosion, there would be a shock wave propagating outward. That's a pressure wave. That's a longitudinal wave. Seismic waves can also be longitudinal waves. And the way that we try to diagram this is a little bit more tricky. We're going to try to use the example of the sound wave, right? Let's start out with a speaker. So let's diagram out a speaker. And in this speaker, we're going to have an oscillation back and forth like this. So the oscillation of that speaker was sideways, back and forth like that. And what we saw in the simulation, going back to that real quick, is that as the speaker oscillated, it created pockets of high pressure and then low pressure, high pressure and then low pressure. So let's go ahead and diagram this out. Here is a high pressure region, and this would be a low pressure region. This is a high pressure region, and this would be a low pressure region. Right? So we can label these and say, okay, this would be high pressure here, here, and here, and then we'd have low pressure here and here. All right, and that's a longitudinal wave. Let's now move ahead and let's look at how we quantify waves. Because what we really want to do is try to start measuring these things. What can we measure about waves? how can we describe waves? How can we measure waves? And what we're going to do now is we're going to draw a graph of a wave, okay? So let's start with a vertical axis, and this vertical axis is going to be the y position in meters of the wave, and then on the horizontal axis, we're going to have the x position of the wave also in meters, just like that, okay? And what we want to do is graph the wave like this. We're going to do a nice sine wave, like that, okay? So what we want to do is ask ourselves, what can we measure on this wave? Now the first thing we want to measure is what's called the amplitude. The amplitude is what you might call the height of the wave. From the x-axis here, which we might call the equilibrium position on the wave, how far above the x-axis does the wave go? We call this the amplitude A, okay? So we're going to write amplitude, capital A, we measure it in meters for this wave, and we're going to say this is the max displacement from equilibrium. Okay? Now if you look at this wave, you might notice that there's more than one place to find the amplitude. The amplitude is also found over here, or over here. Now what about below the x-axis? This is also an amplitude, just as this is also an amplitude. Okay? So we see here how to measure the amplitude of the wave. The next thing we want to look at is something called the wavelength. And this is arguably the most important quantity to measure in a wave. The wavelength lambda is the distance from one crest. Let's label these crests. The crest is the highest point of the wave. So that's a crest, that's a crest, and that's a crest. And the lowest point is called a trough. So that's a trough, and that's a trough right there. Now, if we measure the distance from one crest to another crest, we would call this distance lambda. That's the wavelength. So let's write this down. The wavelength is lambda. Now, this is a Greek lowercase lambda, and it kind of looks like an upside down Y. So think about a backslash like this, and then this little tail coming off the front. That's a lambda. The unit for lambda is meters, and the wavelength is the length of one full cycle of the wave. So that can be measured from crest to crest, as you see there, but it could also be measured from trough to trough. So if I start at this trough and go over here to this trough, this also represents a wavelength lambda. Now, another way to measure lambda is from equilibrium position over to equilibrium position. Now, if I went from this point here to this point here, that would not be a full wavelength. In fact, that would only be half a wavelength. But if I start at this equilibrium position here, go one full cycle of the wave to this position over here, this length here is also lambda. Now, if I had drawn this a little bit more symmetrical, these lambdas would be exactly the same in length, but you get the idea. All right, very nice. Another thing we want to measure in a wave is called the wave period. The wave period has the symbol capital T, which reminds us of the rotational period capital T, or also the oscillation period capital T, and this is measured in seconds. And this is the time for one full oscillation, or I should say one full wavelength to pass a point in space. All right, that's the wave period, capital T. All right, we can also measure something very important called the frequency. And the frequency is a very, very critical aspect of a wave. Now, you encountered this word frequency when you studied oscillations. The frequency is a lowercase f. The unit is the hertz. And remember that 1 hertz is equal to 1 oscillation per second. And the frequency represents the number of repetitions of the wave, or the number of cycles of the wave, or the number of wavelengths, that's a full cycle of a wave, the number of wavelengths that pass per second. That's the frequency, how many wavelengths pass per second. And one important little exercise that we explored when we did oscillations that might be worth reviewing here really quick is the idea of the relationship between the oscillation period t in seconds versus the frequency f in hertz. So I want to ask you this question. Let's say that a wavelength takes 0.1 seconds to pass a point, okay? So it takes 0.1 seconds in order to have one full wavelength of a wave. The question is, how many full wavelengths could we fit in 1 second? So once again, if it takes 0.1 seconds for one wave to pass through, if we had a whole second, how many could we fit in that whole second? That's similar to asking, if you had 10 cents, how many 10 cents could you fit into a dollar, right? And the answer is obviously 10, right? We would say if it takes 0.1 seconds or $0.1, we could fit 10 of those in a second or 10 of those in a dollar, right? There's 10 dimes in a dollar. What about this? What if it took 0.2 seconds for a full oscillation of the wave? How many could we fit into 1 second? Well, how many times does 0.2 go into 1? Or in other words, how many times does 20 cents go into a dollar? Goes in 5 times. So if each wave takes 0.2 seconds, then we can fit 5 of them in a second. What about this? What about half a second? If it takes half a second for a wave to pass, then how many could you fit per second? Well, that's 2. 2 hertz, 2 waves per second. What about 1 second? If it takes 1 second for a wave to pass, then that's going to be 1 wave per second, or 1 hertz. What about this? What if it takes 2 seconds for a wave to pass? If it takes 2 seconds for a wave to pass, can you fit a full wave in 1 second? The answer is no, but you can fit half of a wave per second. Now, if you look at this relationship between the oscillation period, or the wave period, and the frequency, you might recall from oscillations that they are related by the equation F equals 1 over t. And you see that in order to get the frequency, all you have to do is take 1 over the oscillation period, or the wave period. So for example, 1 over 0.1 is 10. 1 over 0.2 is 5. 1 over 0.5 is 2. 1 over 1 is 1. 1 over 2 is 0.5. And because of this relationship, you can also write that the wave period t is equal to 1 over f. You might remember that little algebraic trick where if you have a quantity on one side of the equation equal to a fraction, you can flip the denominator of that fraction with the quantity, and that works here as well. So you can see that this works as well. If you want to find the oscillation period, you take 1 over the frequency. So 1 over 10 is 0.1. 1 over 5 is 0.2. 1 over 2 is 0.5. So it works both ways. And we can say, of course, that this is a reciprocal or an inverse relationship. All right, cool. So the next thing that we want to explore is something called wave speed. Wave speed. And wave speed gets the symbol lowercase v, And what it represents is how fast the wave is traveling. Okay? And just to give you some examples of some wave speeds, the speed of sound, which we write as v sub sound, is pretty fast. 340 meters per second, which is almost 800 miles an hour. Whereas the speed of light is equal to 300 million meters per second. So you can see that they're both waves. Sound and light are both waves, but obviously one travels a lot faster than the other. What I'd like to do now is show you the equation for how to calculate the wave speed. Now, wave speed, like all speeds, can be calculated as distance over time, right? Now, the question is, what unit do we use for the distance of one full cycle of the wave? Well, we use lambda, right? Lambda is the wavelength. It's the length of one full repetition of the wave. What letter do we use for the time that it takes for one full cycle to pass a given point? We use capital T for the wave period. So this is one way to calculate the wave speed, but it's not the most important way to calculate it. What I'd like to remind you is that earlier we derived this relationship where we said T is equal to 1 over F. That means we can substitute this T in here as follows. Instead of lambda over T, we can write lambda over 1 over F. And we all know that if you take a number and divide it by a fraction, same thing as multiplying by the reciprocal. So this is equal to lambda times F over 1, which is equal to lambda F. And what we have just done is derived the wave speed equation V equals lambda F. Please put this in a rectangle, please star it, and perhaps even smiley face it. And you might label this the wave speed equation. And this is a great way to calculate wave speed. Another way to calculate wave speed is simply distance over time. You never know. A problem might ask you, if a certain distance is traveled by the wave at a certain time, you might be able to use V equals D over T. But often we use V equals lambda F to calculate the wave speed. Okay, good deal. Now, one thing I want to share with you is something very, very critical. And that is that wave speed is constant as long as the medium through which the wave travels is constant. Okay? What do I mean by that? What is a medium? If you're an artist, you might know this word medium. You might be a painter, you might be a sculptor, you might be a visual artist with computers. Your medium is the material that you use to create your art. So the word medium in physics means the material or the stuff through which a wave propagates. So an ocean wave is going to propagate through water. A sound wave coming from my vocal cords right now is propagating through the air and it's being picked up by the microphone. Light waves don't need a physical medium, they just travel through space. So on a clear night, if you look up at the stars, you're going to see light coming to you from those stars. That light has traveled, in some cases, thousands, millions of light years in order to come to your eye, and they travel through empty space. So you don't need necessarily a physical medium. Sometimes space itself is enough of a medium for a wave. Now, the reason that this is so important is because if you were to look at the equation V equals lambda F, and if we were to claim that V is constant, so I'm going to write constant under V right here, I want to ask you the following question. If I were to increase the frequency of the wave, what would have to happen to the wavelength in order to balance this equation? So again, the left side of the equation has to stay constant, right? If we increase the frequency of the wave, what has to happen to the wavelength in order to balance the increase of the frequency? If you said the wavelength has to decrease, you're absolutely right. So let me show you an illustration of this using our simulation. So let me jump over here. Okay, so take a look at this wave, okay? We have here a frequency, right, on this wave. It's traveling up and down. And look at the wavelength. Let me see if I can slow this down a little bit. Oh, no, that's not what I wanted to do. Here we go. Let's see if I can slow this down a little bit. Okay. All right. So the wavelength is the distance from one crest to another crest, right? So get a sense of how long that distance is. Now I'm going to increase the frequency, and take a look at what happens to the wavelength of the wave when I increase the frequency. Here I go. So as you can see, I increased the frequency and the wavelength got smaller. And that goes back to exactly what we said about how when you increase the frequency, the wavelength has to get smaller. Let me increase the frequency even more. Here we go. And now you can see how short that wavelength got. Okay? But notice, the wave is still traveling at the same speed. Regardless of what frequency I choose, the wave itself is still traveling at the same speed. Okay? Now, I want to go back to this. I want to really take a moment and focus on this, because this illustrates a critical property of waves. If the wave speed is constant, then we can conclude that lambda, the wavelength, and f, the frequency, are inversely proportional to one another. That means as one goes up, the other has to go down. So specifically, let's say I double the frequency. If I double the frequency and I keep the wave speed constant, that means the wavelength is going to be half as much. And that's always going to be true as long as the wave speed remains constant, and that's if the medium remains constant. Okay? Very good. This is fantastic. Let's move ahead. The next thing that we want to study is sound. Okay? Sound is a pressure wave that propagates through matter, and it has to be through matter. You can't have a sound wave in outer space. You need a physical medium like gas or liquid or even a solid to transmit that sound wave. There's an expression, I can't remember what movie it's from, but they say, in space, no one can hear you scream. And that's true, unless you're in a spaceship that's, oxygenated with air. There is no ability for sound to transmit through space. You need physical matter. You need a gas, you need a liquid, you need a solid to transmit that sound. And just like with all waves, sound starts with an oscillation. So right now, you are hearing the sound of my voice. And my question to you is, what's oscillating? What's oscillating to produce the sound? Well, a couple of things are oscillating. First of all, my vocal cords are oscillating. When you speak or you sing, feel your vocal cords. They're literally oscillating back and forth. So let's write that down. Examples would be vocal cords. Okay? Now, my vocal cords are oscillating. That means that the air is oscillating from here to the microphone. There's a microphone on that camera. And your speakers are also producing sound. So speakers also produce oscillations. If you look at a speaker, what you're going to see is this speaker cone, this membrane, this very thin membrane that oscillates back and forth. and that's what produces the sound. Whether it's in your computer or on your TV or in your AirPods, there's always a little membrane that's oscillating back and forth that produces the sound. And then your eardrum picks up the oscillation. Your eardrum oscillates in response to the oscillation in the speaker, and then that transmits that frequency to your brain, and your brain interprets that frequency as pitch. Very cool. Other things that produce sound are all collisions. Anytime there's a collision between two physical objects, so for example, my hands, when my hands collide, in the clap that you heard there, there's a sound. So what's oscillating? Well, the molecules in my skin cells, when they collide, they oscillate for a quick, split second. And when they oscillate, they produce that reverberation of the air molecules that we interpret as sound. So let's try to diagram this out. We're going to diagram a sound wave by starting with a speaker. And I'm going to very briefly jump back to our simulation to illustrate a sound wave like this. Okay, so everybody can see this here, right? Okay, so let's try to diagram this out the way that we see on the paper. All right. We will diagram this by starting with the air molecules. So we're going to have some dense air molecules, which I'm going to represent like this. So these are going to be high pressure air molecules. Then we'll have some low pressure air, followed by high pressure air like that. Then low pressure, and then high pressure. Okay, so hopefully you can see that pretty well. And what I'd like to do is illustrate that the distance from a high pressure to another high pressure region is actually the wavelength lambda. So that's a lambda, and that is also a lambda there. Okay? Now, if we were to graph this, we'd be graphing the pressure as a function of distance. So for this wave, we start out with high pressure here, then we go to low pressure, high pressure, low pressure, and then high pressure. Okay? So this would be a high pressure region, low pressure region, high pressure region, low pressure region, high pressure region, right? Okay, very nice. We have sketched our own sound wave. All right, another thing that we can talk about here is that the frequency of the wave, which is equal to 1 over the wave period, is represented by the pitch. So frequency is equal to the pitch of the sound. So the higher the frequency, the higher the pitch. All right. The last thing that we want to represent here is the Doppler effect. And the Doppler effect is very, very cool. Let me start out with a video to kind of illustrate the Doppler effect. Have you ever been on the side of the road? Maybe you hear an ambulance passing and you drive over to the side of the road, you park your car while the ambulance passes. Maybe you've noticed that when the ambulance passes you, when it's coming towards you, it's kind of a high pitch. It's like, but then as soon as it passes you, it goes to a lower pitch. It's like, so it kind of sounds like this, right? Or if you've ever watched a video of a NASCAR race, when the cars are driving toward the camera, it's a high-pitched sound, but when they're passing the camera, it's a low-pitched sound. It kind of sounds like this, wow, wow, right? Now, there's a way to think about this, and this video that I want to show you is very, very helpful. Okay? Let's see if we can pull up this video here. There it is. Okay. So in this video, you're going to see a car, and the car is emitting waves. So maybe it's honking its horn, or maybe it's just the engine, but you see these waves. Now, what's important about the waves? Because the car is traveling forward, notice that the wavelength between these high pressure regions is shorter in front of the vehicle than it is behind the vehicle. And the reason for that is that because the car is traveling forward, these waves get compressed. They get bunched up, okay? Let's try to illustrate that in our own diagram here. Okay, so let's jump back over to our notes. let's draw our own version of this diagram. Let's draw a physics car, which of course looks like that. And let's draw a velocity vector for this car to indicate this car is traveling to the right. Now, what I'm going to ask you to do is very tricky. Let's draw a little dot for the horn of this car, okay? And I want to draw some circles that represent the sound waves coming off of this car. Now, notice how we drew these sound waves. They're bunched up, they're compressed in front of the car, but they're spread out behind the car, okay? What that means is, for an observer, like a person standing on the side of the road, the person's going to hear a different frequency than somebody who's behind the vehicle. And the reason for that is that the wavelength, lambda, the wavelength gets compressed. The wavelength gets compressed because the car moves toward the observer. Okay? Now, what about the frequency? If the wavelength gets compressed, that means the wavelength gets shorter. Let's look at the equation v equals lambda f, the wave speed equation. Now, the medium is the air. The air is the medium through which the sound wave is traveling. If the medium is constant, we're not changing the air at all. If this is constant, the question is, if the wavelength gets compressed, that means the wavelength gets shorter. If the wavelength goes down, what's going to happen to the frequency heard by this person? The frequency is going to go up, right? That's the inverse relationship between wavelength and frequency. So this person here is going to hear, this person hears a higher frequency due to the motion of the car. So that means the Doppler effect is the change in frequency of a wave due to the relative motion between the source of the wave and the observer. All right? What if the person instead were behind the vehicle? So let's say there were a person behind the vehicle, in which case the vehicle is moving away from the person. Well, you see here that this wavelength is more spread out. A bigger wavelength means we're going to have a smaller frequency, and that means a lower pitch. Okay? So the next time you're on the side of the road and either a car is passing you very quickly or a siren from an ambulance is passing you, listen for the Doppler effect, because I think you're going to hear it. All right. Thank you guys for watching. If you have any questions, please post them below, and good luck.